5.3 is a pretty important section, fundamental, I guess you could say. We're looking at the fundamental theorem of calculus, and we're going to see what it says. There's actually two parts to it, and we're going to look at an example that shows when this comes up. So, suppose we have the function f of x, and we would like to know the area under the curve f of x. It would be nice if we could find area as a function of x instead of having to use those summations and limits to find our areas. So question is, what is our area function look like? So we don't know how to find this, but we could consider some values of x and some values of the area, and then perhaps we could see what the shape of the area function would look like. If we're going from 0 to x, we want to look at this area. So if we go from 0 to 0, then we're just talking about this single point at the origin. The area is 0. So here my question is from 0 to x. If I go to x equals 1, now I'm talking about this area, and the area is 1/2 because we're talking about a small triangle there. If I go from 0 to 2, now we are looking at that triangle. Area here is going to be 1/2 base times height. The base is 2, the height is 2, so 1/2 base times height is 2. Okay, if we move up to 3, now we are up to there, so we have 1/2 base times height is going to be, I'm going to write it just 1/2 times 9. I think I'll write this as 1/2 times 4. Okay, next one, if I move up to 4, then what is our area from 0 to 4? Well, it's going to be 1/2 base times height, or 1/2 times 16. So could we come up with an area function? How about we do this, 1/2 base times height, or 1/2 times 1. Could we come up with an area function from 0 to, let's just call this value right here, from 0 to x? What kind of pattern do we see here? Well, if we were to sketch the area function, our area function is 0, 0, 1, 1/2, 2, 2, 3, 4. 9/2 is right there at 4.5. 4 would be up to 8 up there. And what does this function look like? I could do better. You say it looks like a parabola. Okay. So it looks like the area function for f of x equals x is some kind of x squared function. That'd be nice to know, because now if we have a way to get this function, then we don't have to use the limit of the sum every time to calculate our areas. Well, this brings us up to the first part of the fundamental theorem of calculus. We're getting closer, but we're not quite up to areas just yet. So first part of the fundamental theorem says if f is continuous on the closed interval and the function g is defined by the integral. Okay, so this is like our area function, a of x. is defined by the integral from a to x. So we're finding basically we're finding the area from a to x of f of t dt. Then it's continuous on the closed interval, and it's also differentiable on the open interval with the derivative of g is equal to f. Well, that's very interesting. What do we know about the derivative of an x squared type of function? Well, using the power rule, we get a linear type of function. So that seems to match what we just saw up there. How are we actually going to use this? What do we need to know? What do I need to tell you about? Well, notice here we're using a variable t as our variable, because in the end we want our area function as a function of x. So first question says, if we have a function, then what is the derivative of this function? So let's look back to our fundamental theorem part 1. If f is continuous on the closed interval, so we're looking at the square root of 1 plus x squared. Is it continuous? Yes, it's continuous for all real numbers. There's no problems with the domain of this square root function because this is always going to be positive. So no problem there. It is a continuous function from 0 to whatever we decide to pick. Then it says, okay, if we've got this set up, which we have, step 2, check. This function, g of x, is continuous and it's differentiable. And the derivative of g of x is f evaluated at x. So what is our f of t in this problem? Our f of t is the square root of 1 plus t squared. So the question is, what is g prime of x? Well, if we look at the fundamental theorem, it says if we meet all the conditions, g prime of x is just f of x. So there's f of t. So what's f of x? There's f of x. And we're done with the problem. That's it. That's all we have to do. Check the conditions to make sure the fundamental theorem part 1 applies. And then if we want to take the derivative, we can just write the derivative. We don't usually define functions like this in a math class, but you will see them more and more as you go. And this is just one example. It's called the Fresnel function. And the question is, what is s prime of x? So you look at the f of t, and you say, well, the sine function is a continuous function. The inside of the sine function, that composite function, everything looks fine there. The setup goes from 0 to x, that is from a to x. So the derivative of this is the sine of pi x squared over 2. And that's it. We're done with that function as well. The next one is a little bit more tricky because we need to play with it a little bit in order to get this to work. A couple things to notice is that the secant of t function is not continuous everywhere. If you remember, the secant of x graph is related to the cosine graph, right? Cosine starts up here, does something like this. Secant graph would have a graph that looks something like that. Okay, so is there any problem from 1? Where's 1 on this graph? This undefined is at pi over 2. Pi over 2 is like 3 point something over 2. That's not 1. So we're trying to find the area function, or the derivative of the area function, I guess you could say, from 1 to x. So there's no problem there. It's continuous between those two points. All right, so that's not a problem. What about the top? Hey, that's supposed to be x, not x to the 4th. So what we need to do when we find the derivative, so we're going to call g of x is equal to the integral from 1 to x to the 4th of the secant of t dt. What we're going to do to take care of that is we're going to have to do the chain rule. So what's the chain rule say? The chain rule says the derivative of, if I think of it like this, instead of g of x, if I thought of this as a g of, well, let me call it something new. If I call it f of g of x, where the inside stuff is an x to the 4th instead of an x, then what's the chain rule say the derivative of f prime to the 4 is? Well, you would say the derivative of this is a chain rule. It's the derivative of the outside. Let me do this. What is the derivative of this thing? It's the derivative of the outside function with the inside still inside times the derivative of the inside function, which is a power rule. So, in our problem, what does that do? It means we have to do the derivative of the outside function is the secant of stuff times the derivative of the inside function is, oh, that's not a 3, that's a 4, 4x to the 3rd. So that's it. We just have to use the chain rule, and basically if that isn't just x, we're using chain rule. We're substituting this x to the 4th in place of our t, and then we've got the inside derivative there from the chain rule. That's the fundamental theorem part 1.